Hey team, Connor here from HPA and welcome to another one of our webinars. This week we're going to be talking about the mass, stiffness and strength of wheels and basically what ends up being the most important for automotive performance or motorsport applications. So what we commonly see here is people liking to use a lot of buzzwords around wheels like lightweight wheels or unsprung mass or forged wheels, for example, without a really clear understanding of what these actually mean and what's really going on and how it translates onto our vehicle. So today we'd thought we'd have a little bit of a chat about how the design and manufacturing process play into these aspects, and then how these aspects are all related to each other as well, and then the effects that this actually has on the performance of our vehicle and what this all means. We are primarily going to be talking about aluminium alloy wheels because these are by far the most common that's used in motorsport. We will touch a little bit on carbon fiber and steel wheels as well, but generally we're talking about aluminium alloys. So we'll get started with the first one, and maybe the most basic to understand, being strength. So basically the strength of our wheel is essentially how much stress the wheel can withstand before it breaks. So that really outlines impact strength more than anything. So if the wheel takes a hit or it's loaded up, how much stress it can take before it fails. The other thing to consider here is also the fatigue strength. So this kind of comes from repeated cycles. As we know, I imagine our wheels are subject to repeated loading from bumps or just cornering forces and so on. So this really comes from stress concentrations or cracks, micro cracks in the surface, which eventually begin to propagate and get bigger and bigger until they're big enough where the wheel fails altogether. So basically, if we talk about the strength of a wheel, every wheel that's produced, or should do, but will generally be able to support basic driving. So driving down the road, normal driving around the city or on the highway or so on. But what it can handle past this is very different, and this is where it kind of separates between a wheel that's maybe suitable for motorsport application to that's maybe fine for grandma's grocery getter, for example. So wheels are, the scary thing about this is there's not really any good standards or common standards that are used everywhere internationally for the strength of wheels. TUV in Germany and JWL from Japan are some good standards, but this is not always required depending on what country you are in and where the wheels are being sold. The load rating, which is on the wheel, can give some indication of the strength of the wheel. A wheel with a load rating of 600 kgs, for example, you could probably take away from that will be stronger than perhaps a wheel that has a load rating for 400 kgs, but it's not usually as kind of clear cut as that. In terms of those load ratings, what we want to do is basically never use a wheel that has a load rating lower than what that corner of the vehicle will see. So basically when we're doing something like this, if we're purchasing a new set of wheels, we'll look at, say, the load rating. If it's 500 kgs for that wheel, we will look at the maximum axle weight of the vehicle, front axle or rear axle, whatever is heavier between the two, divide that by 2, and that number must be lower than the load rating of the wheel. And that doesn't mean that 500 kg load rating wheel is going to fail at 500 kgs. That's just what has been deemed the safe kind of maximum load rating on that wheel for normal driving and so on. So the strength of the wheel itself is primarily governed by the grain structure, also the design of the wheel. We'll start off with the grain structure here. So the grain structure is really a result of the manufacturing process of the wheel. So if we talk about the different manufacturing processes of the wheel, probably the most basic or entry level is being cast. So that's what we see here on the far left of my screen. And what we end up here with is a grain structure that's kind of randomly orientated, all different sizes and so on. It kind of looks like squiggles here, but it's basically lots of little grains randomly orientated and yeah, no real structure to it. If we move on to a machined part here, which some wheels are the centers, for example, are machined out of billet aluminium, if we're talking about a 3-piece wheel. And what we have in a machined part is we have this grain flow, but then as we machine it, we basically break the ends of the grains here. And what this does is, one, it makes with a wheel, the structure with the grains aligned like that tends to be a lot stronger than a cast part. But as we break the ends of the grains here, this leads to is micro cracking on the surface of the part. And in the end, that can kind of lead to issues with fatigue strength and things like that. And then if we move on to a forged part here like this, this is when we have what's called true grain flow. So where the grain flow follows the shape of the part or the shape of the wheel in our example. So it'll be aligned with the wheel structure, and that's really how we get the most strength out of the material of the part. If we talk about flow-formed or flow-forged wheels, that's a common kind of marketing word that's used around the manufacture of wheels now. And basically what this means is that some areas of the wheel, for example, like the barrel of the wheel, will be forged in some method. So basically we end up with some areas of the wheel having this true grain flow. Generally this kind of sits somewhere in between a forged wheel and a cast wheel. Parts of the wheel are forged, but not all of the wheel, like a fully forged wheel. So yeah, that's the basics around the strength of the wheel and what kind of governs that strength, and why a forged wheel ends up being stronger is because of this grain flow being aligned with the shape of the part. From there, we'll move on to mass, and we're going to come back to each of these and talk about how they relate a little bit more as well. So mass is basically, or the weight of the wheel, is why we use aluminium wheels in performance applications over something like a steel wheel, in most cases anyway. Less weight is almost always better. So all other things equal, of course, we're usually looking for a lighter wheel. The thing about the reason for this is basically because any mass of the vehicle, be it from our wheels or any part of the vehicle, unsprung or sprung mass, which we'll get to in a moment, that all contributes to load transfer. And what we want to do for grip is minimize that load transfer. So as we go around a corner, load is transferred onto the outside tires, and as that load is transferred, our total grip decreases. And that's by means of something called tire load sensitivity. Basically how the coefficient of friction between the rubber of the tires and the road surface changes as with the vertical load on it. We won't get too deep into that, it's a pretty complex topic. But basically what we're trying to do is minimize the load transfer. And one way to do that is minimize the mass. So let's get on to talking about unsprung mass. So unsprung mass is basically the mass of our vehicle that isn't supported by the suspension springs. So this will be our wheels, tires, our braking system in most cases, the hubs, and then partially parts of our suspension arms as well. But wheels make up a huge part of that. So what our suspension is trying to do while it's working is basically maintain the contact patch between the tyre and the road and make that as consistent as possible. If we have lighter wheels, it takes basically less force to move that contact patch. So essentially our suspension can do a better job and soak up from bumps and recover from bumps easier and keep that contact patch a lot more consistent and flat on the road. Another advantage of having that lower unsprung mass there means that we can basically, or a run-on from this is that we can end up running a lighter suspension spring and less damping as well to control that. And that's all positive because basically it gives us more flexibility in the setup, and we have less compromise for between comfort and grip. The other thing that is something that was mentioned in that podcast I talked about in the intro to this webinar with Joe Scarbo is that in off-road applications, if the vehicle, for an off-road vehicle, they typically have a very heavy unsprung mass, and then that needs a heavy suspension spring to be able to control that. And then basically what you end up needing then is a heavy truck to be able to handle that force as well. So it's kind of like a ongoing or spiraling effect of everything needing to be heavier just because the unsprung mass is heavier. So it's kind of a funny way to look at it, but you end up needing to have a heavier chassis to control that spring that is needed because the unsprung mass is so heavy. So if we end up with a lighter unsprung mass, we can use a lighter spring, and then the vehicle doesn't need to be as heavy as well. It's a kind of different way to look at it as to what is normally the case on a on-road or road racing application. Moving on from there, So we'll move on to another thing past unsprung mass is the rotating inertia. So when we talk about inertia, it's basically the rotational momentum or that force from the mass as it rotates of our wheels. So if we have more mass, or the mass is distributed further out from the axis of rotation, that ends up being more inertia. So a bigger overall diameter or a heavier wheel or tyre will lead to more inertia. And the same thinking, if we think about the same outer diameter and we talk about a 17-inch wheel with a thicker sidewall on the tyre, or we talk about an 18-inch wheel with a smaller sidewall on the tyre, this is a little bit tricky to kind of decide here what's going to have more inertia, and it tends to be more by a case-by-case kind of basis. And it's a little bit more tricky to measure than just putting the tyre on a scale as well. But basically, rotational inertia, it acts like a flywheel essentially attached to the engine. If you have had any experience using a lightweight flywheel on an engine, you'll notice that the engine can rev up faster, and it also, to a small amount, means a lighter flywheel will mean more torque gets through the engine and we have less losses. And the wheels are basically exactly the same story here, because once we're in gear and rolling, it's all connected to the engine and drive line, just like a flywheel is as well. So in the end, less rotational inertia means better acceleration. It's easier to speed up the rotation of the wheels. It's also easier to slow them down, so we have better braking performance as well. The last thing I wanted to talk about on the topic of mass is the gyroscopic effect. So, in very simple terms, this is a rotating wheel's tendency to maintain the direction of its rotational axis. So basically what that means is if we have something spinning, it doesn't want to change direction, so that rotational axis will move. And this is part of the reason why a bicycle is easier to balance the faster it rolls. And it's also, if you've ever played with a fidget spinner, I tried to bring one in today, but I couldn't find one. The little thing that you spin around in your hand, and as you spin it, you can feel the inertia as you spin it, and that gyroscopic effect preventing you from changing the direction of its rotational axis. So this resistance to change in direction basically means the steering of our wheels. So if we have a higher gyroscopic effect from a heavier wheel or more rotational inertia, we end up having slower and heavier steering, and it also damps the feedback that we get through the steering as well. So our feel gets a little bit damped, and we don't have such good feedback. So the way to think about this, I guess, is if the feedback force coming through, how that compares to the actual force from the gyroscopic effect. So if that gyroscopic effect is a larger thing, then as that force comes through, that'll be smaller, and we won't be able to distinguish between those two as much. basically what we get is a numb feeling through the steering wheel the heavier the wheels get. And the more that gyroscopic effect comes into play, but it also means that the change of direction takes more force as well. And this might be fine for a cruiser or maybe in some cases an off-road car, but it's not really what we want for a race car where handling is important. So some more comments on the mass is that the manufacturing process in itself only has a very small effect on density. So if we have the same size part and it is cast or it is forged and the design is exactly the same, there will only be a very small effect on the density and therefore the mass of the part. The difference comes into the fact here is that a forged wheel can weigh a lot less because it has the inherent strength behind it to have a different design, where the design might have more material removed, for example, and that's what actually makes it stronger. It's not that a forged material is lighter than a cast material. It's probably a little bit more in the other direction there. So before we move on to the next topic of stiffness, if you have any questions, feel free to ask them in the chat and I'll do my best to answer them at the end. Let's move on to stiffness, and this is where I find it gets a little bit more interesting. I'll just bring up something on my screen in a moment. So stiffness, to put a definition on it, is basically the resistance to temporary deformation. So basically how much it resists flexing. So there's a few different scenarios here, and I'll try to show them in one of these videos, which I have this one here. So we can see in this one here that we basically have the inside of the wheel here, the mounting points, winding up relative to the barrel. So that's one form of stiffness that we need to be concerned about. But in reality, that has a very little practical effect in practice. It does make a slight difference for delaying acceleration or braking, I guess, a little bit, but in reality not so much in practice. This is not the stiffness that we're really worried about. What's more important, there's another form of stiffness there, is the barrel actually flexing like that, and again that's something that maybe you'd feel a little bit, but in practice it's not so important. So I'm not sure if it's shown in this video. I think it is, yeah. So as we come to the side view here, we actually get this deformation of the wheel here. So when we're going around a corner and the tyre is pulling or pushing on the bead seats of the wheel, it's actually flexing the wheel like that around the hub. So basically the reason this is important, and I'll get on to explaining that a little bit more, is that some aluminium wheels have basically been found to flex up to 1 degree here, and basically what that does is it changes the camber of the wheel. So if you imagine, this is called camber compliance, and it basically works just how rubber suspension bushings work, and why we'd move to something like a poly bushing or a solid bushing like a spherical bearing or something to reduce that camber compliance, to gain a more consistent alignment. So basically if we think about going around a corner, let me wind back a little bit. Said some aluminium wheels are known to flex enough to lose 1 degree of negative camber. That is 1 degree per 1 G of cornering force. So if you're cornering at 2 Gs, you'd lose 2 degrees of negative camber. So for example, if we pulled 1.5 Gs around a corner, which is something pretty achievable on a slick, more than that is obviously very achievable as well, then we need to basically run an extra 1.5 degrees of negative camber to make up for that, so we have the same contact patch as we get around the corner, and basically that's going to compromise our straight line performance, so acceleration or braking performance as well, and also our tyre wear. And yeah, basically it gives us the same feeling past that of kind of vague handling that we'd get from old rubber bushings as well. I had another image here, so I think this was off Moto IQ when they were testing some Carbon Revolution wheels, and you can kind of see that shown a little bit more, where they have, in this case, said big name aluminium wheel, flexing enough to lose that 1 degree of camber, and then they have the carbon fiber wheels here as well. And carbon fiber wheels, obviously, we'll get to those in just a moment, but they're really stiff. That's kind of the main benefit of carbon wheels, or that their strength to weight ratio as well, or stiffness to weight ratio more rather. So a comment on the manufacturing process of the wheel there is that the grain structure itself, be it, you know, good grain flow from a forged process or random kind of grain structure from a cast process, has no impact on the stiffness of the material. So basically, if we're talking about the same alloy and it's a forged wheel with exactly the same design as the cast wheel, the forged wheel won't be stiffer in that case. However, it's the design of the wheel that is the primary means of achieving the stiffness. And basically, why that's important for the manufacturing process is a forged wheel has more inherent strength again, so it allows for a more flexible design process, and then basically what that means is that more flexibility in the design process, you can design a stiffer wheel from that. The reason, so basically, the takeaway from that is that stiffness is extremely important to the precision and the compromises in the handling of the vehicle and the contact patch and our camber compliance. Maybe more so than having just a lightweight wheel. But if we think about how wheels are marketed, it's a lot easier for a manufacturer to advertise and sell a lightweight wheel because it's so much easier to measure and understand than something that's high stiffness. But in the motorsport world, what we'll typically see is wheels that are actually a little bit heavier, but significantly stiffer than their kind of road going or retail counterparts for this reason exactly. Okay, so again, any questions that come up, I'll do my best to answer them at the end. Some important points to remember here is just because it's a forged wheel, it doesn't mean that it's lighter or stronger or stiffer than a cast wheel. The manufacturing process has very minimal effect on the weight and the stiffness. It's an inherent strength of the manufacturing process of using something like a forged wheel that allows that for more flexibility in the design to be able to achieve a lower weight wheel or a higher stiffness wheel. But all three of these aspects are considered together, and all three of them are very important. Strength is clearly important because of safety, and it allows for more design flexibility. Weight is very important because it allows the suspension to control the contact patch better, which basically means we get more traction and grip. There's less inertia, so we have better acceleration and braking, and less gyroscopic effect, which means we have better steering response and better feel as well. And then finally, the stiffness is important because we get less camber compliance, and then therefore we have less compromise in the wheel alignment specs. So final point I want to make here is on replica wheels, because this is such a controversial topic. So morals aside, if the design of a wheel is perfectly copied, then it will probably weigh the same, and it'll probably have the same stiffness as well as the original wheel. And this basically comes down to the manufacturing process. So typically a replica wheel will copy a forged design, but it will be cast, and therefore what we run into is issues when it comes to the safety of the wheel in terms of strength. However, the same thing can be said kind of the other way around. An older genuine cast wheel could be copied with a new manufacturing method, still being cast, but new alloys and new techniques. And in that case, maybe the new wheel or the replica wheel could in that case be stronger than the original wheel. So it's really just a case-by-case basis. Finally, carbon wheels are extremely stiff and have that really low weight, so that's kind of the key benefit there. However, a carbon fiber wheel, it's obviously not cast or forged or anything like that. Carbon fiber wheels are typically made with pre-preg carbon fiber in an autoclave, and that is a seriously expensive process, and therefore the wheels themselves end up being extremely expensive. In terms of the design of the wheel itself, I know that we've mentioned that a few times here, so I just wanted to bring up this here from Titan 7. So this is their forged 5-spoke. It's a split spoke in this case, and it's generally kind of accepted that this split spoke design here, and that's similar to what's shown if we go over the overhead. Under the overhead here, this is a little 3D print of a BBS LM or E88. I'm not 100% sure, but it's the same thing here, split spoke design, and that's kind of generally considered the optimal design for strength to weight and stiffness as well. And in terms of the wheel design and how that process works, I actually had the chance to talk to the guy from Titan 7 at World Time Attack recently, and we did a bit of an interview on this, which hopefully will be coming out eventually, and just talked about the use of FEA and simulation, and also what's known as topology optimization or generative design, to design the structure of the wheel like this. And I'm not sure if there's an image here which I can show, but yeah, there's a lot of pocketing and things that go on like this in modern wheels that do a lot to reduce the weight without taking away from the strength and the stiffness of the design as well. With that covered, I'll jump into the questions, and then when we have wrapped up that, I'll just go on to show another one of our courses at the end that, if you're interested in this topic, might be of interest to you. Alright, John, I know the general statement is that reps are bad, however people seem to buy second-hand reps somewhat often thinking they are genuine. Is there any way to tell the difference on most wheels? Okay, so I'm not an expert on this, but I will say a few things that I've picked up, and this is generally around Japanese wheels, so if we're talking about a T37 for example. One of the key ones that I pick up on is if the wheel has made in Japan on it. That's a good tell. Typically, some of the ones that aren't replica wheels will have Japan written on them, or they'll have Japan design written on them, but they won't have made in Japan written on them. There are some other features that they might have, like bead knurling and things like that, or certain pocketing on the back of the wheel that is a process that takes extra cost to put in, but might not be something that's really picked up by the average enthusiast. So things like that might stand out as well. But I will generally say, if you're looking at a specific set of wheels that's often replicated, then do an online search, and someone's probably put together some forum somewhere saying, hey, these are the key differences between the real one and the replica one. A lot of wheel companies now have gone to using things like laser engraving and things like that, that the kind of gets around what the more budget orientated manufacturers will avoid doing that, just because it's adding extra cost to their wheels, and they're just trying to get them done cheaply and sell as many as they can. Hopefully that helps a little bit. Okay, Thomas, does running wheel spaces affect the stiffness and strength of a wheel? If so, how much would be safe to space the wheel out? So I don't think it affects the stiffness of the wheel itself, but it definitely affects the stiffness of the suspension that it's bolting it to. So basically, That's the reason why running spaces kind of ends up damaging wheel bearings and things like that. It's kind of putting more of a lever arm on the suspension, on the bushings and all things like that. So you do end up with a bit more deflection in the upright and the bushings and so on. In terms of strength, it's kind of the same thing. It's a tricky one here because I've seen, factory built race cars like TCR cars and things like that coming from the factory with spacers on them. It's definitely not a bad thing. A lot of people kind of explain it as some frowned upon thing that you should never run a wheel spacer, and that's just not true. In saying that, it kind of all depends on the setup of the vehicle. Maybe nothing more than 20 millimeters would be excessive. So we try to keep it something under that, for example. Also, if you're spacing the wheel out a lot, one of the kind of key impacts that has on things is actually the scrub radius. So on the front of the vehicle, the more you space it out, the more positive the scrub radius is going to get. If you're starting with a negative scrub radius and bringing that out, it might not be a problem, but you kind of don't want to end up in a space where you're making that front scrub radius over 40 millimeters or something like that is going to end up giving you issues if it's a front wheel drive with torque steer, but it's also going to give you issues with bump steer and things like that on any vehicle as well. We talk about the scrub radius and how to measure that and find that out in our wheel course, which I'll talk about in just a moment. But yeah, to answer your original question, I would say the stiffness, a spacer does not affect the stiffness of the wheel or the strength, but it does put more load through the suspension, which is going to mean things flex a little bit more and are a bit weaker as well. Again, Blake, does offset of the wheel affect the strength? Yes, it does, but that is something that's factored into the design of the wheel from the manufacturer. So it's hard to generally say that one wheel is going to be weaker than another wheel because it has a higher offset, because the manufacturer might have designed the wheel with a different shape spoke or something like that to make up for that. But where the mounting face of the wheel is in relation to the wheel would definitely affect how the load is transferred through the wheel and therefore the strength. So, Caleb, is there any benefits to going to a multi-piece wheel? The benefit around a multi-piece wheel is typically around the flexibility of the specs of the wheel. So, basically, it allows the manufacturer to develop a wheel with a wider range of specs, different widths, offsets, and so on, simply by using the same center and using different lips or barrels or halves, whatever you want to call them. So that is kind of the key benefit there of using a multi-piece wheel. Also, if you damage the lip of the wheel, you can just replace the lip, for example. It's not something that's typically, generally, if we're just talking about what is going to be the stronger or the lightest and the best stiffness wheel, it'll typically be from a wheel that is a monoblock or a single piece, typically forged wheel. Aesthetics is another thing there, but that's all personal preference, of course. Similar question here, I think, from Goriup. I heard 3-piece wheels are more flexible than a single piece. Would a steel barrel and a magnesium center not get you closer to the best compromise? Yeah, but steel barrels are obviously a lot heavier than aluminium barrels as well. I know, just thinking off the top of my head, a wheel like, I think it's a Ronal wheel called the Eclair, or it might just be that's what the brand is. They have stainless steel lips and they're very heavy. And then you're talking about using a magnesium center, which I assume would be to offset that weight. You're still going to end up with more weight further from the center of rotation, which gives you more rotational inertia than perhaps having more mass closer to the center. So yeah, there's still a compromise, I think, there. Again, typically if we're just talking about the best stiffness and weight, it'll usually be from a single piece wheel. Yeah, so that's all the questions. Hopefully that answered some of those. giving you a little bit more insight into it. And I'll just jump back over to my screen here. And before we wrap up, I just wanted to talk about our wheel and tyre fitment course, which we have here as well. So if I just jump down to the curriculum in this course, we'll just run through a little bit about what's involved in this course, because it is an area that a lot of people think they're experts on, but generally we see it gotten wrong more often than not, I'll say that. Some pretty surprising ideas of what people think is good wheel fitment out there, and it doesn't just come down to aesthetics, it's also the function of the vehicle as well. Typically our approach to this is around maximizing performance, but if you're anything like me, then you'll find that the best aesthetics come from a functional setup as well. So as you imagine, tyres are one of the most important aspects of the vehicle when it comes to performance, and wheels are basically the foundation for these tyres to do their work, so they are naturally very important to performance as well. So let's just run through the curriculum here. Basically start off with the fundamental knowledge of wheels, so structure, construction, materials, manufacturing techniques, and mounting methods. So some of what we've covered today, but going into it in a lot more detail as well. Then we talk about all the different aspects of dimensions and sizing for wheels. So the simple ones like the diameter, the width, different lug patterns, center bores, and so on. And we also talk about camber and camber gain as well, and how that affects our wheel and tyre fitment. Then we move on to talk about performance factors, so all the aspects of a wheel that factor into performance: mass, stiffness, and strength, those three top ones, what we just discussed today. But talking about it in a little bit more depth, and we have, of course, in the course the benefit of animations as well to help transfer some of that knowledge, make it a little bit easier to visualize as well. We also talk about balancing wheels, or the balance of the wheels, track width, scrub radius, brake clearance, and bead security features. So I think these two here, track width and scrub radius, have a massive impact on the performance of the vehicle, and that's something that people often don't consider when they're just talking about wheel fitment and trying to get the best kind of fitment on their vehicle in terms of from an aesthetic standpoint anyway. Brief discussion on legalities, because depending on where you are in the world, that might be something you need to consider. We can't always just run the exact wheel and tyre size that we want. We also touch on tyres just slightly. It's not a tyre course. Tyres are an extremely complicated subject that would really require its own course, but it needs to be mentioned here. And then we get on to some practical skills here as well. So how to measure a wheel, how to measure a car for fitment, how to choose the correct size wheel and tyre for your specific vehicle, and once you've got that wheel and tyre, how to check for clearance as well. And as we do those, we provide that all as worked examples on real cars that we have here at HPA to help show you how those skills are applied in a real situation. Then we also have a 3-step process, just kind of bringing all the knowledge of this course together to help you basically be able to choose any tyres for any vehicle that you're working on. So yeah, I'll leave it at that. That is our wheel and tyre fitment course if you're interested in learning more about this topic. But yeah, I'll leave it at that, and we'll be back next week with another webinar. So we'll see you then, and thanks for joining us today. That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added to our webinar archive where our Gold members can watch them at their own leisure. We currently have over 380 hours of existing webinar content covering topics on engine building, engine tuning, wiring, suspension and car setup, fabrication, and CAD. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as stay up to date with the latest tools, trends, and techniques in the performance industry. Our Gold members also get access to our private members only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you will receive 3 months free access with a purchase of any of our courses. Click the link in the description to learn more.